Hi everyone. We all know that LLMs like GPT-4 are powerful, but many of us, the architecture remains a black box. We know what it does, but not exactly how the math handles the language. So for this project, which is part 3 after attention the theory and attention math, I wanted to strip away the high-level frameworks like PyTorch or TensorFlow. I built the core engine of a transformer, the self-attention mechanism entirely from scratch using linear algebra and NumPy. The goal is to mathematically prove how a static word like animal evolves to become more context aware. So we're going to run this notebook together. Let's start by the libraries. So the first challenge is that the computers don't read words. They read vectors. So I started by simulating static word embeddings, essentially a dictionary where every word is a list of random numbers. But for a bag of words isn't a sentence. For example, the dog bit me, and the man bit the dog look identical to computer if you just sum them up because they have the same words. So to fix this, I implemented positional encoding. I used the sine and cosine wave formula from the original paper Attention All You Need. This injects a unique mathematical fingerprint, let's say, into every word based on its order. So the model knows what the here the came first in the sentence. Okay, so now let's generate the initial embedding. Now for the positional encoding that we talked about. So now we get to the heart of the transformer, the attention mechanism. I manually implemented the query key value projection layers. Think of it like a database lookup, like the query queue. What is this token looking for? The key K, what information does this token hold? And the value V, what content will I actually pass along? By taking the product of the queries and keys, I calculated the similarity score. This tells us how much attention every word should pay to every other word. And since I wanted to simulate a generative model like GPT, I ran into two problems. The first word was cheating by looking at the last word. So to fix this, I built a look ahead mask. If you so we don't look at the future text. So let's unlearn the mask, and now for the multi-head computation. Let's see, these are what we just talked about. The mask, of course we use the softmax probability, and then we use the dot product. Let's visualize one head, like the animal did not cross. These are like the weights or the context translated into words. As you can see, this logic is wrapped into a multi-head loop, just like humans look at a sentence for both grammar and meaning simultaneously. I initiated two heads, The first head one might focus on vocabulary, the second might focus on the sentence structure. I concatenated these results into one final vector. Z. The result, like the final vector of the word animal, was no longer just the static input, but it was a mathematical weighted sum containing, let's say, 20% of did, this percent of not, cross, etc. The word has successfully absorbed its context. So this project allows us to look under the hood. In real world, we use, of course, pre-made models, open source models maybe, and tools, or even libraries like PyTorch, TensorFlow, but this was all from scratch, just to see the simple once we understand the mechanism. So if you understood this, you will have a foundational understanding of the linear algebra that powers today's LLMs. This is the graph of the architecture that we use, two heads, and then we do the softmax, and then matrices multiplication. So yeah, this is it. Thank you for watching. Please like and subscribe.